So the next lecture in the energy and momentum unit is on simple harmonic motion, section 4.6 in your textbook. So when we push a spring, either extend it or compress it, that restoring force pushes it back to its equilibrium position. Now, oftentimes, we do not have the object go back into the position and just stop at that equilibrium position. What may happen is the restoring force will push it towards the equilibrium position. It will move past the equilibrium position, and then an opposite restoring force, a restoring force in the opposite direction, will then push it back towards the equilibrium position, and then it will overshoot that equilibrium position, and then it will kind of rotate back. And we have this kind of motion where it's oscillating around that equilibrium until it finally comes at rest at the equilibrium point. And we call that simple harmonic motion. Now here's a graph kind of showing something like that. Imagine we had a pen attached to a spring, and the spring's kind of oscillating back and forth. That output looks like a sine wave, and it's actually true in that you will see periodic motion, and often you'll see sinusoidal motion when we're looking at simple harmonic motion. So that what's labeled here are things that you should know from your previous physics class. The labels are the period of a waveform, which goes from a peak to a peak, or a crest to a crest, or a trough to a trough. The amplitude, which is the distance from the equilibrium point to the maximum displacement. And then we have crests and troughs. We also, in this case, it's showing the direction of motion of the paper. So that is as we kind of go towards the right on this graph, we're looking at going forward in time. So as the time increases, the oscillation occurs, and we will not have an oscillation forever. Oscillation will eventually die down. So while it appears sinusoidal, and there are periods where it will be sinusoidal, there's also quite often a dying down of the motion, and we'll get into that. That's called damping, and we'll get into what that is, how it's caused, and how we define it later on in this lecture. So periodic or nearly periodic motion is seen everywhere. They give some examples here and where you would see it. What's interesting is we've been talking about this with springs, simple harmonic motion, but this actually occurs quite regularly in other applications. One of them in electrical engineering and electronics design. You may know that in digital electronics, 0 volts often represents an input of 0, and 1 volt or 5 volts often represents an input of 1 in a binary coded system. Getting from 0 to 5 volts is not, it's instantaneous in terms of our purposes, where we're looking from a macro level, but on the smaller electronic level, there is a little bit of an overshoot in terms of the voltage, and then there's a settling of the voltage until it finally gets to that 5 volt or 0 volt measurement where it needs to be. The length of or the I guess the amplitude of that overshoot and the time it takes for the signal to settle are important aspects in electronics design. So while we're looking at simple harmonic motion mainly from the idea of a spring here, if you continue on in physics, you'll see this in many, many other applications. So please copy this down. Simple harmonic motion is the periodic motion in which the acceleration of the moving object is proportional to its displacement. F equals K delta X. So just remember that. The force is our spring constant times our delta X. And that's our restoring force, and that often is a force that can push us past the equilibrium point. And then we will have to, the force will act in the opposite direction. It will push past the equilibrium point and then operate in the opposite direction until we finally get a point where we settle at our equilibrium. So let's look at a vibrating guitar string. At what times would this string be vibrating with the greatest speed, and what times would it be at the least speed? Or rather, when is it moving the fastest, when is it moving the slowest? Now, at the A and B points, at those amplitude points, we have a change in direction. This was something that you saw in the first quiz in the dynamics unit. A change in direction means that our velocity goes down to 0 and then goes in the opposite direction. So if it was positive before, it becomes a negative velocity. If it was negative before, it becomes a positive. That 0, our slowest possible speed, occurs at the maximum displacement points, A and B. Now the force that's acting at A, we'll see this on the next slide, is the strongest because the displacement is the farthest away from the equilibrium point C. So with that greater force, we end up having our speed starts to increase at A, and it continues to increase until we get to C. At C, we're at our greatest speed, either in the up or down direction. If it's coming from A, it's in the down direction. If it's coming from B, it's in the up direction. But once we're moving from A to C, we have our greatest speed at C. The speed is now still going in the down direction towards B, but now the force of the spring is operating in the opposite direction. So it starts to slow down our string until it reaches B and it changes its direction. So this next slide asks, when do we have the greatest acceleration? And the greatest acceleration occurs when we have the greatest force, because F equals ma. So our greatest force, as I said previously, is at A and B because we have our greatest displacement from our equilibrium point. The least acceleration is at C. The greatest kinetic energy occurs when we have our speed being the greatest, and that maximum speed occurs at C. So this is just to get you to understand a little bit about simple harmonic motion, and I think this example actually comes from your textbook. The greatest potential energy is at A and B. So the energy at A and the energy at B is equal. The energy at C is also equal to the energy at A and B. So at C we have our energy is completely kinetic. At A and B our energy is completely potential, elastic potential. That energy transfers its mechanical energy, so at any point between A and C or C and B, the sum of the elastic potential and the kinetic energies are the same. But at A and B, the kinetic energy is 0, and at C, the potential energy is 0. When describing simple harmonic motion mathematically, you can picture a circle and a reference point. So here we have a rotating CD, and as this mass that is attached to our spring moves back and forth around that equilibrium point, the point on the CD rotates with uniform circular motion. So we will always have a periodic function in terms of where our mass is in terms of the equilibrium point, or where our CD is rotating in terms of the reference point. So at all points on that CD, if we rotate that CD and we graph that, what we'd end up with is a sinusoidal function. And if you want to see this a bit more in depth, page 198 covers this. Now, simple harmonic motion is the period of simple harmonic motion, because we have a sinusoidal function, and because the a circle is 2 pi radians in terms of distance that would be traveled around a circle, we can actually calculate what the period is of a certain spring, what that will experience simple harmonic motion, using a function that's shown here. T equals 2 pi square root of m over k, where m is our mass and k is the spring constant. So what happens in this case is we are reducing, so the n over m and the kg that we have in our mass will divide together to produce seconds squared, and then we'd have to square root that to find out how many seconds we have, and then multiply that by the distance traveled, which is 2 pi, and that gets us to our period, which is just in seconds. Now, this is the simple harmonic motion equation for a spring, which is what we'll be looking at mostly in this course. There are other equations for other applications, but they're all very similar, involving square roots and 2 pi. Now, this equation as well doesn't show up on your formula sheet, so I would recommend writing that down on your formula sheet now, just so that you're aware of it and you're not looking for it during a test. So here's a question. It says, a car mounted on the springs in its suspension acts like a mass on a spring. If the passengers are added to the car, will the frequency of oscillation increase, decrease, or stay the same? So looking back at that simple harmonic motion equation, and I'll just zoom back here just to show you, T equals 2 pi square root of m over k. Frequency is the reciprocal of that. So because we're asked about frequency, so we have to imagine that equation as a reciprocal. Because the frequency is proportional to the square root of the reciprocal of the mass, then when the mass increases, the frequency will decrease. So explaining this with the equation would be acceptable. The more passengers we add to the car, the less the frequency of oscillation will be. Here's another problem. It says, suppose a diver with a mass of 85 stands on a diving board with a spring constant of 8,100 newtons per meter. If we ignore the mass of the board, what is the period of the board and the frequency at which the board vibrates? So the period of the board is 2 pi, and then I'm going to have to do the square root, so I'm going to put brackets times the square root of our mass, which is 85, divided by our k value, which is 8,100. Now to do the square root, I'm just going to raise this to the power of 0.5, which is equivalent to finding the square root. And I get 0.6436. That's in seconds. I have to round to 2 significant digits, so I get 0.64. To find the frequency, I need to find the reciprocal of this. So often your calculator will have a button like this, a 1 over x button, or an x to the power of -1 button. Pressing this once will just give us the reciprocal, which is 1.55. Rounding for 2 significant digits gives 1.6 hertz. I just want to check something really quick. 1.64 So that would work in this case, but sometimes it's important not to use our, if we use our rounded values, we'll sometimes get the wrong answer when we're finding reciprocals especially. Here's a question. It says a mass spring system undergoes simple harmonic motion. The elastic potential energy at maximum stretch is 7.5 joules. The mass is 0.2 kilograms and the spring constant is 240. So calculate the frequency and the amplitude of oscillation. So to find the frequency, I will first find the period. So 2 pi times 0.2 divided by 240, and that is brought to the power of 0.5, same as the square root. This is our period. Our frequency is 1 over that, which is 5.5. Now it says the elastic potential energy at maximum stretch is 7.5, so we need to find the amplitude of oscillation. So this, we're going back to our equation for elastic potential energy, which is 1/2 kx squared, or 1/2 k delta x squared. So if we know our potential energy is 7.5, and we had a 1/2 on the right side of the equation, so we'll multiply by 2 to get rid of that. We will divide by the k value, which is 240, and then we'll find the square root of this. We end up with 0.25, which is 25 centimeters. So that was done using the elastic potential energy equation, which is 1/2 k delta x squared. So your textbook talks a little bit about perpetual motion machines in this section, and we can define a perpetual motion machine and determine how it is impossible using simple harmonic motion. So it says here an ideal spring will never lose energy. It would continue with simple harmonic motion forever, or as long as you do not disturb it. A machine that can continue to operate for an unlimited amount of time without outside help is a perpetual motion machine. So a grandfather clock is not a perpetual motion machine because you must wind it up every now and then. So if you may not be familiar with grandfather clocks, but they're clocks that operate for long periods of time without a battery, but their energy comes from a winding mechanism. That winding has to be done, and when it is fully wound, or when it's even half wound, time is measured accurately. As it gets closer to the end of the winding, the time starts to slow. So 1 second on the clock starts to get closer to 2 seconds, and starts to get closer to 3 seconds, and that tells you that it's time to wind the clock and reset the time. So this question says, is a perpetual motion machine possible? So it would not be possible because we do not have an example. There's no such thing as an undamped simple harmonic motion system, because there's always going to be friction that's caused in the system that is going to dissipate some of its mechanical energy into the atmosphere somehow. There could also be loss of energy that's from the sound, from light, thermal energy. Any sort of loss of energy in a simple harmonic motion system will cause damping, which will prevent it from being a perpetual motion machine. So that's a perpetual motion machine. A perpetual motion machine is a machine that can continue forever without restarting or refueling. It's impossible since some energy will always be lost from the system. I'd ask you to write that down. We're going to have some communication questions in this course, and that will require some writing. So while some of these things that I'm asking you to write now, they are not algebraic or mathematical in nature, they're important to know for multiple choice questions and for any explain type questions that you'll have. So I've referred to damping a bit, and what damping is is you can think of it as a settling down of a system. So this image that we have here of a graph, we have a, you can imagine that this was a sinusoidal function or sinusoidal simple harmonic motion. The x-axis is our time, and the y-axis is our displacement, either above or below our equilibrium position. So when y is equal to 0, our delta x, our displacement from our equilibrium, is 0. But when y is above, it's a displacement, it could be above or to the right or whichever sort of convention you're using. When y is below, it's the opposite displacement. So displacement in the opposite direction that we had defined in the context of the question. So when we get to a point where the system starts to lose energy, we have this dampening effect. And when we're looking at dampening, anytime we're above the equilibrium position, we call it an overshoot. So in this case, we have our first major overshoot, and then we have an undershoot, and then an overshoot, then an undershoot. But we often define this just with overshoots. We have 5 that are displayed here. There is a time when we will have a settling occur, and depending on your application, for physicists, the settling occurs when our displacement is at 0 and we do not have any more oscillation. For engineers, often they count settling time as being within 102% to 98% overshoot. So the system could still operate with a little bit of oscillation around the equilibrium position, but that type of oscillation that we're allowed depends on the system we're looking at. So damped harmonic motion, you can write this down. It's periodic motion in which the amplitude of the vibration decreases with time. So there's a loss of energy. This is quite often due to friction in mechanical systems. In other types of systems, it could be sound or heat or some other type of energy. So there are 3 ways of defining damping. There's actually a 4th that is the ideal case, the perpetual motion machine case, that's called undamped. So let's look at each of these. So we have our number 1, that's our overdamped system. So what we see here is a slow settling towards our equilibrium position. So there is no overshoot in an overdamped system, but it takes a long time, or it takes a longer time to reach our settling time than it might in other systems. Now, an overdamped system will often feel like it takes a long time to resolve. You might have experienced this, for example, if you've used a balance, a mechanical balance or electronic balance. Sometimes with electronic balances, you'll place something on the balance to measure its mass, and you'll see it might say something like 35.1 grams, 35.2 grams, 35.3 grams, then 35.4 grams, and it'll finally settle at that. That's an overdamped system. That takes a long time to settle. The critically damped system is our best case. So understanding that we do not have undamped systems, the critically damped system gets us back to our equilibrium position at the fastest possible time. determining the critically damped damping effect is quite often important for a mechanic who is designing, or maybe a mechanic who's setting a shock absorber in place, or a designer of a shock absorber who's trying to make sure that these shock absorbers make the ride as smooth as possible. The critically damped system will get to its resolve time faster. So in terms of what each of these three types of responses look like, the faster we get to a flat line on the 0, the better the system is, depending on our applications, but that's what it is in most cases. Now, the underdamped system has a large overshoot, and the overshoots after that start to decrease. So depending on the system here, we can actually have, and depending on our parameters, we can have a fast response, a faster resolve time with an underdamped system versus an overdamped or critically damped system, if our parameters are not as strict. So when I was talking about the electronics earlier, we had 0 volts and 5 volts. Those are often, when we're talking about a digital binary system that's electronic based, 0 volts represents a 0, 5 volts represents a 1. The electronics themselves will sometimes even represent something like a 3.2 volts as a 1 volt, or a 6.8 volts as a 1 volt, or as a 1 output. So in terms of the output voltage needing to be a 5, it doesn't have to be exactly a 5, but if it's close to 5, then that's good enough. Electronics require calculations to be done very quickly. So they're often set to be underdamped responses, with the caveat that the overshoot is not too high, not to damage the electronics, and also that the settling time is short enough so that it's better to use the underdamped system than it is to use the critically damped system. And the undershoot for an undamped system is important as well, because if that undershoot goes past the 3 volts, for example, it might start to alternate the signal from a 0 to a 1 back to a 0, whereas we wanted it to go from 0 to 1 and stay at that 1. So I want you to understand overdamped, critically damped, and underdamped. They are very important for this course, or rather for this unit, and you will see something like this in a future test. So please copy this slide down. You could read the rest of this lecture, and again, if you have any questions, feel free to ask me on the course website.